Welcome back. In this video, we'll talk about analysis of variance, specifically when you might use it and how it works. So analysis of variance is really a generalization or an extension of the t-test to allow for more than two groups. So we use analysis of variance if we want to know if there are differences between the means of at least two groups and if there are specific groups that are different from the others. So let's start with just the null and alternative hypothesis that an ANOVA model is trying to test. ANOVA stands for analysis of variance, and that's the term that I'll use from this point forward. Essentially, we have our data split up into K groups, K more than 2, and we'd like to know whether or not our groups have the same population mean. So our ANOVA null hypothesis is that mu1 is equal to mu2 is equal to mu3, and so on. In other words, all of our observations are assumed to start with the same value. Then any difference that we're observing can be attributed just to random variation. Our alternative hypothesis is that there's at least one group that differs significantly from the others, again, based on the mean response. So for some I not equal to j, the mean of group I is not equal to the mean of group j. What this alternative doesn't tell us is which groups are different. So it's kind of like a chi-square test in that regard, in that we know that some groups are different, we just don't know which ones. The ANOVA model states that our individual observations, y sub ij, can be written as three components. So we take an overall mean, or a grand mean, we call that mu. We add some effect of being in group I, we call that alpha sub I, plus some random error term epsilon. So let's say that we have the data set below and we want to do analysis of variance or ANOVA to see if the mean in group A is different from the mean in group B or is different from the mean in group C. So here's our 12 observations. Each of these bars represents just a single observation. So we have 4 bars indicating values for group A, 4 bars indicating values for group B, 4 bars indicating values for group C. Now, first we need to find the overall mean, or the grand mean. Our best estimate of this is just going to be the overall mean of all 12 data points. So that overall mean is 11.58. That's our best estimate of what the population mean might actually be. So I'll add that to the plot. We see that group A is below the mean, group B is kind of in the middle, group C tends to be above the mean. Now what I need to do next is measure, well, how far each of these groups actually is from the overall grand mean. So I'll group my observations up into group A, group B, group C, and look at those means. So group A has an average of 7.75. That means that group A is on average 3.83 units below the overall mean. Group B has an average of 11.5, so on average group B is pretty close to the mean, just a little bit below. Group C is on average a little bit higher than the overall mean. This is a typo, by the way, this should say above. So here are these group differences compared to the mean. So group A falls right about here. Group B falls right about here. So we're explaining a lot of the differences just looking at these averages. Now, we don't quite capture the original observations. The next thing, or the last thing that we want to do, is measure the errors. So for each observation, we'll calculate how far that actual point is to the group mean. So these red lines indicate the error terms, or how far we're off. Are we explaining more of what's happening in the data with these individual error terms? Or are we explaining more with the group differences? That's what ANOVA is really trying to measure. So we fit this ANOVA model using the AOV function in R, AOV for analysis of variance. We'd like to see how our Y variable depends on the groups. We get a p-value of 0.004. So yes, it looks like there is strong evidence to show that the mean of at least one group is different from the mean of the other groups. That's basically how ANOVA works. There are some assumptions with this. The first assumption is that the model parameters are constant, so that grand mean mu isn't changing. Those group effects alpha, they're not allowed to change either. And then finally, there's a parameter here called sigma squared. That's measuring the variability of the error terms. So whatever these underlying numbers that we're trying to estimate are, they're fixed, they're constants. The second assumption is that the ANOVA model is additive. So we're only really looking here at linear combinations. We can add factors together, we can add terms together in the ANOVA model, but we can't raise things to a power, for example. The third assumption is that these error terms are independent and identically distributed. So the error terms do not affect each other. They're also assumed to follow a normal model with mean 0. So some observations will have a positive error, some will have a negative error. And then finally, the population variances for each group, or the factor levels, are assumed to be equal. So let's look at an example. A study done in the Journal of the American Medical Association included 3 groups, each with 25 subjects. The control group consists of healthy individuals with no history of brain trauma who are comparable to the other groups in age. Second group consisted of college football players with no history of concussion. Third group consisted of college football players with a history of concussion. We used this data in a previous video to look at how brain hippocampus volume changed from each group. Now we want to use an ANOVA test to look at an overall measure of differences. So here's our research question. Does playing football affect the size of a person's hippocampus? Our null hypothesis is that the mean hippocampus volume is the same for all 3 groups, so mu1 is equal to mu2 is equal to mu3. The alternative is that the mean hippocampus volume is different for at least one group compared to the rest. We want to take a look at this data. Clearly, there are some major differences in hippocampus volume. The control group is a lot more variable, so that might be something that we worry about. ANOVA does assume that all groups have the same variation or standard deviation, so that could be a problem. The concussion group tends to have much smaller hippocampus volume than the no concussion group and the control. So first, we'd like to estimate these group effects and the grand mean. So we've got the overall mean football or mean hippocampus volume, got the mean for each group. So here are the estimated group effects. The grand mean for the entire data set is 6,598.8. The group effect for group 1, the control group, is positive. They're above the mean, 1,003.8. Group 2 is below the mean. This is the concussion group. Group 3, football players without a concussion, they're much closer to the mean. The test statistic for an ANOVA test is called an F statistic. This F statistic is essentially the ratio of 2 measures of variability. So we calculate something called a mean squares for group, or MS group. This measures how much variability there is between levels of each factor. So it's a measure of how different the control group is from the concussion group is from the no concussion group. The mean squares for error then measure the variability within each level. So how much variation is there in the errors? Now, if all of the groups are exactly the same, then there shouldn't be much variation between those group means. So MS group should be pretty small, and the F statistic should be pretty small. So small F statistics will help support the null hypothesis. Large F statistics will be better evidence for the alternative. Now, anytime you fit an ANOVA model in software, you get a table that looks like this. It's called an ANOVA table. The basic outline is always the same. The calculation details are in the textbook. What I'd like to do is go through just the most important parts of this table. So the first column are the degrees of freedom. More than anything else, I like to use this degrees of freedom table or column as a sanity check. So this should contain in the groups or in our variable or treatment row, whatever the number of groups is k minus 1. So if we have 3 groups, this should have 2 degrees of freedom. The total should be the sample size minus 1. The error degrees of freedom should be n minus k. So we can use this to confirm that our data has been entered into the model appropriately. The F column will just spit out the test statistic, the F statistic for you. The p-value column will give you the p-value. The sums of squares and the mean squares, you don't need to worry about how those are calculated. So let's apply this to the hippocampus data. So we'll fit an analysis of variance model or an AOV model to see how brain hippocampus volume depends on group for the football brain data set. There's a very small p-value, so there's some very strong differences in this data. So I will reject my null hypothesis. There is strong evidence to show that the mean hippocampus volume depends on whether or not someone has played football and experienced a concussion. Now, we don't know which groups are different yet, just that some groups are different. What we've just done is called the one-way analysis of variance model. There's just one explanatory variable that's being considered. In a two-way ANOVA, we'll add a second variable. So here's what that second variable model looks like. We have a group effect for our first variable, which we'll call factor A, and a group effect for our second variable, which we'll call factor B. So we're just adding more terms to this model. In a two-way ANOVA model, we've actually got 2 null hypotheses that we're going to test at the same time. We'll write these in terms of the group effects. So for factor A, the null hypothesis is that all of the groups are the same. We'll say that there's A levels of factor A. For factor B, we'll say that all of the group effects betas are the same. The alternatives are that for each factor, at least one level is different from the others. The two-way ANOVA table is a little bit bigger. It's just going to have 2 rows. It will have 1 for factor A and then 1 for factor B. So let's take a look at an example with two-way ANOVA. So the owner of a restaurant in Potsdam, New York was studying tipping patterns of his customers. So over a 2-week period, he collected data from 157 bills at the restaurant that included the amount of the bill, the size of the tip, the percentage of the tip, so PCT tip, number of customers in the group, whether or not a credit card was used, day of the week, and an identity of the server. So was it server A or server B? Here's our question. Will the waiters get bigger tips on certain days? Will the waiters get bigger tips if the customer pays with a credit card? I'm going to use percentage tip here. Please ignore this prompt being written twice. Apologies for that. So our model is that our tip or our percent tip Y has some overall mean plus some effect of whether or not a credit card is used plus some effect of the day of the week plus some random error term. So our null hypothesis for the credit card is that alpha 1 is equal to alpha 2. For day, there were 5 days, so this restaurant wasn't open every day of the week. So beta 1 is beta 2 equal to beta 3, beta 4, beta 5. Here is our result. So we'll see how percentage tip depends on credit card plus day. It looks like credit card is not a big difference. Credit card didn't really affect the tips. Day of the week didn't affect the tips either. So there's no differences. Now watch what happens if I switch the order here. So right now I've got credit plus day in my model. If I switch it to day plus credit, my conclusion doesn't really change, but these p-values have changed slightly. What happens is how R, or what causes this is how R is estimating the ANOVA table. Now, if there's the same number of observations, the order in which we write these variables won't actually make a difference. But if the factor combinations do not have the same number of observations, then there will be a small difference. Now in our data set, what it looks like is that, well, first, people at this restaurant were more likely to pay in cash than a credit card. But there's definitely different numbers in each day of the week combination. That means that the ANOVA table won't be the same depending on the order. Now, will it change a lot? No. The things that are going to change are the F values, the P values. So most of the time, these changes aren't enough to make a meaningful difference. No matter which version of this ANOVA table you look at, there's still no strong differences. If you have differences in your number of counts in each observation, I recommend fitting the model both ways. If your conclusion stays the same no matter what, then that's some more support for your decision. If you get differences depending on the order, talk to a statistician. Now, once the model's been fit, you can use a function called model.tables to calculate the overall mean and the group means. So here's the average tip percent, about 16.6. On Fridays, it looks like the tip percent is on average 16.26, Mondays 15.93, Tuesdays 18.02. So there's really not much difference from day to the week. This rep just tells you how many observations are in those categories. Using a credit card versus not doesn't seem to affect the tips either. Now, which of these groups are different? If there were differences between your groups, you could use a method called Tukey's honest significant differences to compare more than one of these groups simultaneously. Now, it's really important that you use a method like this to test or compare the groups simultaneously, because ANOVA is prone to a problem in statistics that we call multiple comparisons. The idea here is that the more tests we're doing, the more likely it is that at least one of them is going to have an error, will result in an incorrect decision. So this Tukey HSD function not only does all of these tests at the same time to compare the groups, but it also adjusts the results to account for that multiple comparison problem. So the good news is that if you use this Tukey HSD function, you can get all of the comparisons at the same time, and we know that they've been adjusted for that problem. So this is really highly useful. What you get from this is for each pair of groups, the difference in tips. So this is the average tip on Monday minus the average percent tip on Friday. You get a lower and upper limit for a 95% confidence interval and an adjusted p-value. So there's really no evidence here that Mondays and Fridays are different. There's really no evidence that any of these days are different. And there's no evidence that using the credit card is different. You can plot these if you choose. So here's what this plot looks like. These confidence intervals all overlap with 0. So if they're including 0, that means that 0 is positive value for the difference, so there might not actually be a difference. Now let's try this with our football example. And we know there's some big differences between the groups, so this result should look a little bit different. Specifically, if we look at each of these three pairs, we have some highly significant p-values. So that tells me that there's some pretty big differences in the hippocampus volume between each of these three groups. Not only that, but we now have a confidence interval for those differences too. So we will stop here with analysis of variance. You'll get some more practice on the practice quiz for this topic and the homework. Next week, we'll talk about correlation. Have a great day.